Thank you for joining today. Our scenario is this. We need to design a fraud detection system for financial transactions. Think credit card or payment transactions. It should detect and ideally prevent fraudulent transactions in real time. I'd like to discuss how you'd design the system end to end. Where would you start?
Sure, this is a critical system. I'd start by clarifying the problem and requirements to make sure we build the right solution. I have a few questions to help scope this out. First, what type of transactions are we focusing on? For example, are we talking about credit card payments, bank transfers, or something else? Second, do we need to make a real-time decision on each transaction to either block or allow it, or is it okay to just flag suspicious ones for later review? Next, what are the latency requirements for a decision? Is there a hard limit like needing a result within a few hundred milliseconds? Also, how many transactions per second or per day must the system handle? This will help us think about scale. And how will we get the labels for what is and isn't fraud? For instance, will fraudulent transactions be confirmed through chargebacks or user reports, which might come in days later? Finally, are there specific goals for accuracy, like minimizing false declines versus catching all possible fraud? And are there any regulatory or privacy constraints we should be aware of, like GDPR or PCI compliance?
Great questions. Let's say it's for credit card transactions in an e-commerce context. The system should make an inline decision before a transaction is completed, potentially blocking it or flagging it for review if it's likely fraud. Latency is very important. We want the fraud check to add at most, say, 100 to 200 milliseconds to the transaction processing. Volume is high, on the order of millions of transactions per day, which means hundreds per second at peak. The fraud rate is low, well below 1%, but each incident is costly. And you're right about the labels. The ground truth for fraud comes with a delay. We often only find out a transaction was fraudulent days later through customer reports or chargebacks. For metrics, the business cares about catching as much fraud as possible, meaning high recall, but without creating too many false alarms that inconvenience legitimate customers, so precision is also key. In other words, we need to minimize false positives while maximizing detection. And yes, since we're dealing with payments, we must consider privacy and compliance like PCI DSS for card data and GDPR if it applies. Does that help?
Yes, that's very helpful. So to recap, we need a real-time fraud detection system that processes each transaction in under about 200 milliseconds, scales to hundreds of transactions per second, and deals with highly skewed data, where fraud might be just a fraction of a percent of all transactions. It should flag or block fraudulent transactions as they happen. The labels are delayed, which means our model training has to handle that delayed feedback. And we have to balance catching fraud with keeping false positives low, all while complying with financial data regulations. Got it. I'd approach this by breaking the problem down into a few key areas. First, the high-level system architecture, especially the real-time versus batch components. Second, the machine learning model and the features for fraud detection. Third, scalability and latency considerations. Fourth, data quality monitoring and the feedback loops we'll need to improve over time. And finally, I'll address trade-offs, edge cases, explainability, and privacy. Does that sound like a good plan?
That sounds perfect. Let's start with the high-level architecture. Can you sketch out how the system would look and the major components?
At a high level, I envision a real-time processing pipeline for the transactions, plus an offline component for model training. For the real-time fraud detection flow, the key components would be: first, transaction ingestion. As transactions occur, they are fed into our system. This could be a direct synchronous call to a fraud check service or an event published to a message stream like Kafka or AWS Kinesis. For scalability, many systems would use a streaming source like Kafka. Next is feature retrieval and computation. We need to gather relevant features for the transaction in real time. This involves fetching data about the user's history, their account, their device, and so on. A feature store can be very useful here. It could be an in-memory database like Redis, storing the latest data for each user. If some features require recent history, like the number of transactions in the last 5 minutes, a streaming computation job could be updating those in real time. Then we have the ML Inference service. This is the core predictive service. It takes the transaction data with all its features and runs it through a trained machine learning model to get a fraud risk score. This service needs to be highly optimized for low latency. It would likely be a microservice using a fast framework like FastAPI or a dedicated model serving tool like TensorFlow Serving. After the model, there's a decision engine. The model's output, say a fraud probability, goes to a logic component that applies business rules and thresholds. For example, if the score is above a certain threshold, we might auto-decline the transaction. If it's in a middle range, maybe we flag it for manual review. If it's low, we allow it. This engine could also have hard rules, like block all transactions from a banned country. In summary, the decision engine combines the model score with explicit rules to make the final call. The next step is the response or action. Based on the decision, the system responds in real time. For a payment, this means sending a signal back to the payment processor like approve, deny, or maybe challenge, which could trigger a request for two-factor authentication. And finally, logging and feedback collection. Every transaction and the model's decision should be logged. This is for two reasons. First, for auditing and explaining why a transaction was flagged, and second, to create training data for the future. We also need to collect the final outcomes. For example, when a human analyst confirms a transaction is fraud, or when a chargeback comes in days later. A component of our system needs to collect this ground truth and tie it back to the original transaction records. Outside of this real-time flow, we'd have the offline model training pipeline. This is where we'd store all historical transactions and their fraud labels in a data lake or warehouse. Periodically, say daily or weekly, we'd run a job to train a new model on the latest data. That new model would then be carefully deployed to the Inference service, maybe with A/B testing or in a shadow mode first. So, in effect, it's a bit like a Lambda architecture, a speed layer for real-time detection and a batch layer for model retraining.
Excellent overview. You mentioned using a streaming service like Kafka. Why would we need that instead of a direct API call?
It really depends on the integration. In many setups, the payment system would call a fraud detection API synchronously because it needs an immediate response to approve or deny the transaction. This is simple, but if the fraud service is slow or down, it directly impacts the payment. An alternative is an asynchronous message pipeline using something like Kafka. This decouples the systems and helps with scaling and buffering traffic spikes. However, for a truly real-time decision, a synchronous check is usually required. A hybrid approach is also possible. The payment service could call our fraud service synchronously for the immediate decision, but also push the event to Kafka for other offline analytics. Given our requirement to prevent fraudulent charges before they happen, I would lean towards a synchronous call to a highly available fraud detection service. Internally, however, that service might still use streaming mechanisms to fetch features quickly.
That makes sense. Now, you touched on feature retrieval. Let's talk more about features and data. What kind of data would this system use, and how would we get the necessary features in real time?
Good question. The model's effectiveness is hugely dependent on good features. We have several data sources we can use here. First, we have the transaction details themselves. Things like the timestamp, amount, currency, merchant ID, payment method, device ID, and IP address. These are immediately available. Then there's the user's profile and history. This includes their past transaction history, average spending amount, typical transaction frequency, and usual location. We can create aggregated features from this, like the user's average transaction amount or the number of transactions in the last 24 hours. We also have the device and location context. Has this device or browser fingerprint been seen with this user before? Is the IP address consistent with their known patterns? A large distance between the user's last known location and the current purchase location could be a major red flag. Next is the merchant information. Certain merchants or product categories might be riskier than others. For example, electronics or gift cards are common targets for fraud. We could have a risk score based on the merchant's history. And finally, we could incorporate external data if available. This could be data from device reputation databases, IP geolocation services that identify known proxies or VPNs, or blacklists of compromised cards. Now, to compute these features in real time, we'd pre-compute as much as possible. We could use a streaming processor like Apache Flink to continuously calculate aggregates, like a running count of a user's transactions in the last 5 minutes, and store them in a fast key value store. When a new transaction comes in, we can do a quick lookup to get these features. Some features can be computed directly from the transaction itself, like the time of day or whether the amount is unusually high. And for device or IP information, we might call a separate specialized service. The feature store concept is really important here. It ensures that the features we use during model training, offline, are computed in the exact same way as they are during real-time serving. This prevents a common source of bugs in ML systems. One challenge is the cold start problem for new users who have no history. In those cases, we'd have to rely more on the transaction attributes themselves and maybe compare their behavior to the average new user.
It sounds like a lot of moving parts. Let's say we have all the features and the model gives us a fraud risk score. You mentioned using a threshold and possibly rules for the decision. How would we determine the right threshold or integrate rules with the model?
The threshold would be set based on the business's tolerance for risk. We would tune it using a validation data set to achieve our target trade-off between precision and recall. For example, we might find that if we set a threshold to flag 0.5% of all transactions, we catch 80% of the actual fraud. The business would then have to decide if that false positive rate is acceptable. It's a constant balance between customer friction and financial loss. As for integrating rules, we could have a two-layered system. First, some simple hard rules could trigger an automatic block regardless of the model score. For instance, a transaction from a blacklisted device should be blocked instantly. For everything else, we use the ML model score. We could say if the score is above a high threshold, we block it. If it's in a middle range, we flag it for manual review, and if it's below a low threshold, we allow it. This way, the really obvious cases are handled automatically, and the gray area goes to human experts. Over time, as the model gets better, we might rely less on the rules, but they provide a great safety net, especially at the beginning.
Good. Now let's shift to the machine learning model itself. What approach would you use to actually detect fraud? Talk about model choice, training, and how you would handle the imbalanced data.
For fraud detection, we're typically looking at a binary classification problem. Is this transaction fraudulent or legitimate? For the model choice, I'd consider a few options. A simple logistic regression would be a good baseline. It's fast and interpretable. However, for this kind of problem, tree-based ensemble models like XGBoost or LightGBM are very popular and usually perform extremely well. They're great at handling nonlinear patterns and skewed data. We could also consider neural networks, but for structured, tabular data like this, tree ensembles are often very hard to beat. As for feature engineering, some of the most powerful features would be the transaction amount compared to the user's usual spending. A large deviation is a strong signal. Velocity features, like the number of transactions or total amount spent in short time windows. Fraudsters often make many purchases in a rapid series. And geolocation anomalies, like the distance between this transaction and the user's last known location, and simple binary features, like whether this is a new device or IP address for this user. Handling the class imbalance is critical here, since fraud is so rare. There are a few techniques we can use. We could use resampling methods to either oversample the fraud cases or undersample the legitimate ones in our training data. We could also use class weights during training, which essentially tells the model to pay much more attention to getting the fraud cases right. For example, in XGBoost, we could set a weight to make misclassifying a fraudulent transaction 100 times more costly than misclassifying a legitimate one. Finally, for training and evaluation, we would split our data by time, always training on older data and validating on newer data to mimic how the model would perform in production. We would evaluate the model using metrics like precision and recall, not just accuracy. We care a lot about recall. How much fraud did we catch? But we also need good precision to avoid flagging too many legitimate transactions. We'd likely look at a precision recall curve and work with the business to pick a threshold that gives us an acceptable balance.
It sounds like you'd lean towards a gradient-boosted trees model with careful feature engineering. How would you train and deploy this model in practice? Walk me through the pipeline from training to serving.
The pipeline would look something like this. First, we'd extract historical transactions and their labels from our data store. Since labels are delayed, we'd use a cutoff. For example, using data from last week where most of the fraud labels have been finalized. Second, we'd perform all the pre-processing and feature engineering. This is a critical step to ensure we don't accidentally leak future information into our features. Third, we'd split the data into training and validation sets. Fourth, we'd train the model using a library like XGBoost or LightGBM, applying techniques to handle the class imbalance. Fifth, we'd evaluate the model on our validation set, checking our precision and recall metrics. Once we're satisfied, we would serialize the model and package it for deployment. This usually means wrapping the model in a lightweight API, for instance, using FastAPI in a Docker container. This container would expose an endpoint that takes transaction data and returns a fraud score. For scalability, we would deploy multiple instances of the service behind a load balancer and set up auto-scaling to handle traffic spikes. When we deploy a new model version, we would do it carefully. We'd start with a canary release, sending a small percentage of traffic to the new model, and monitor its performance closely. We might also run it in shadow mode, first where it makes predictions but doesn't act on them, just so we can compare its decisions to the old model on live traffic.
Good. Now, how do we ensure the system is scalable and maintains low latency at high throughput? Can you talk about performance considerations?
Absolutely. Scalability and latency are top concerns. First, horizontal scaling is a must. The model inference service needs to be stateless, so we can run as many instances as we need behind a load balancer. For low latency, every component has to be optimized. The model inference itself is usually very fast, often taking just a few milliseconds. The bigger bottleneck is typically feature retrieval. This is why using in-memory data stores like Redis for quick feature lookups is crucial. We have to avoid slow database queries in the real-time prediction path. We also need to pre-compute as many features as possible using a streaming processor. This way, at prediction time, we're just doing a simple, fast lookup instead of a complex calculation. We also need to plan for peak loads, like during a holiday shopping season. Using a message queue like Kafka can help buffer traffic spikes. Our services should also be set up to auto-scale based on traffic. Finally, we need to have robust latency monitoring. We track metrics like the 95th and 99th percentile latency of our fraud check service to ensure we are always meeting our service level agreements. If latency starts to creep up, we know we need to scale up or optimize our code.
Good. Now, how do we monitor this system and maintain it over time? And how do we incorporate feedback to keep the model up to date as fraud patterns change?
Monitoring and feedback loops are critical for any live ML system. For system monitoring, we track standard metrics like throughput, latency, and error rates with alerts for any anomalies. For model performance monitoring, it's a bit tricky because the ground truth is delayed. However, we can monitor proxy metrics in real time. For example, we'd watch the fraction of transactions that the model flags. If that number suddenly spikes or drops to zero, something is likely wrong. We can also monitor the distribution of the model's prediction scores and the statistics of the input features to detect data drift. Once the actual fraud labels arrive, we can retrospectively calculate the model's true precision and recall. This gives us our actual performance numbers. The feedback loop is how we keep the model current. When fraud is confirmed, that new label data gets fed back into our data store. We would then have a process for periodic retraining, maybe weekly or even daily, using the most recent data, which allows the model to learn from the newest fraud cases and adapt to changing patterns. We'd also A/B test new models against the current production model to ensure that any changes we make are actually improving performance before we roll them out to all users.
Now, let's consider trade-offs, failure modes, and edge cases. What are some challenges in fraud detection, and how would your design handle them? Please also touch on explainability and privacy concerns.
There are many important considerations here. The biggest trade-off is false positives versus false negatives. A false negative is a direct financial loss. A false positive is a legitimate customer being declined, which hurts their experience and can cause them to churn. To manage this, we can use a tiered response. For transactions where the model is only moderately confident it's fraud, instead of an outright block, we could challenge the user with two-factor authentication. This helps reduce friction for legitimate users. Another major challenge is concept drift. Fraud tactics are always evolving. To handle this, we need regular retraining, as we discussed. We could also have a parallel anomaly detection system that flags transactions that look unusual in a way our current model hasn't seen before. For explainability, it's crucial, especially in finance. We need to be able to explain why a customer's transaction was declined. If we use a complex model like XGBoost, we can use techniques like SHAP or LIME to identify the top features that contributed to a specific decision. We could then translate these technical reasons into human-readable explanations, both for our customer support teams and for regulatory compliance. Finally, for privacy and security, this is non-negotiable. The system handles highly sensitive personal and financial data. We must be fully compliant with regulations like PCI DSS and GDPR. This means encrypting sensitive data both in transit and at rest, tokenizing card numbers whenever possible, restricting access to the data, and having clear data retention policies. The fraud prevention system itself must be secure so it doesn't become a new vector for attack.
Great. You've covered a lot of ground. Now, let's get a bit practical. What tech stack or specific technologies would you use to implement this system?
Sure, let's break it down by component. For streaming and messaging, I'd go with Apache Kafka. It's the industry standard for high-throughput, real-time data pipelines. For the feature store, I'd use Redis for its low-latency reads and writes, likely updated by a streaming job running on Apache Flink or Spark Streaming. For the offline data lake, I'd use a cloud solution like Amazon S3 with a query engine like Presto, or a data warehouse like Snowflake or BigQuery. For ML model training, I'd use Python with libraries like Pandas, scikit-learn, and of course XGBoost or LightGBM. I'd use a tool like MOflow to track experiments and manage model versions. For model serving, I'd build a lightweight service using Python with Fast API, containerize it with Docker, and orchestrate it with Kubernetes for scalability and reliability. For monitoring, I'd use Prometheus to collect metrics and Grafana for dashboards. We'd also set up alerting with a tool like PagerDuty. This stack is modern, scalable, and uses technologies that are well suited for each part of the problem.
That sounds reasonable. One last question. Could you briefly outline how you test and validate this system before and after deployment?
Certainly. Before deployment, we would perform extensive offline validation by replaying historical data through the system to see how it would have performed. We'd also do rigorous load testing to ensure the system can handle peak traffic without a drop in performance. When we're ready to deploy, we'd start with shadow testing. The new model would run in parallel with the old one, making predictions on live traffic, but not acting on them. This allows us to safely compare its performance and catch any issues. After that, we'd move to A/B testing, routing a small percentage of live traffic to the new model and gradually ramping it up if it performs well. And after deployment, we have continuous monitoring. We would also regularly conduct postmortems on any fraud cases the model missed to understand why and identify areas for improvement. This continuous cycle of testing, deploying, monitoring, and learning is key to maintaining an effective system in the long run.
Excellent. You have given a very comprehensive design. You covered requirements, architecture, modeling, and many practical considerations. Thank you. Just to wrap up, is there anything you want to add?
Just to conclude, designing a fraud detection system is a balancing act between speed, accuracy, and trust. We want a system that is fast enough to operate in real time, smart enough to catch evolving fraud patterns, and yet transparent and reliable enough to maintain customer trust and comply with regulations. By combining a solid architecture with a well-thought-out machine learning approach and strong feedback loops, we can build a system that significantly reduces fraud while minimizing the impact on legitimate users.
Great summary. Thank you for walking through this design in such detail. That was exactly what I was looking for.